should probably be doing more problems than I assign. A lot more, yes. Ooh, there's this amazing thing. It's absolutely incredible. It's blue. It's about 300, 400 pages at least. It's called a textbook. All right, so at the end of a textbook are a whole series of problems. Notice I touched none of them. Go in and just pick the hardest problems you can and start. And that'll get you fluent. All right. So, elevator problem, right? That's what this problem was? So, you have a guy in an elevator. And what's going on here? Yeah, so for the first 2 seconds, what are you told?
The scale reading drops from 6 meters per hour down.
No, so initially,
The elevator rises and the scale reading increases from 1,000 meters to 40.
okay, so now what is this telling you? That the scale is rising. Yes. The normal force, correct. So let's actually do a free body diagram on this guy. So here's a free body diagram. And what you have normal force and you have gravity. So Fn, Fg. Any other forces? No. Yes. Woohoo. Who's the body? The person. What does that person feel? Physics is about feelings. What does that person feel?
The scale.
That's it.
Okay.
He feels the scale and he feels the earth pulling down on him. So, now, the scale rises from what to what? So what does that mean? That means that when that elevator was at the bottom, ostensibly, right, that he had a reading. What is that reading giving him? His weight. In other words, initially you have Fn minus Fg equals, well, this is always true, right? This is always true in this case. There's no other forces acting on him. So initially, what's the acceleration of the elevator? 0. So this equals 0. So step 1, Fn minus Fg equals 0, which tells you that Fn equals Fg equals mg. What does the reading here say? It's 1,000, right? 1,000 newtons? Right? So you have 1,000 newtons, and what's g? I tell you what g is. Those numbers are too nice for 9.8. G is 10. So you have m times 10 equals 1,000. It tells you. Sure. So you get m is equal to, how much is m? How much? 100. M is 100 kilograms. Nice. So now we go back, and now it starts accelerating, right? Notice m is 100, Fg is 1,000. So we're going to use that. Because what happens in the first 2 seconds? Accelerates, correct? And what happens to Fn? It goes up to what? It goes up to 1,400. So you have 1,400 minus 1,000 is equal to 100A. So you have 1,400 minus 1,000 is 400 equals 100A, and therefore A equals 4 meters per second squared. Then what? Goes at a constant velocity, right? Notice when it's at a constant velocity, what does that scale say? It says 1,000 newtons, right? Or it doesn't tell you it goes at a constant velocity, right? It just tells you that the scale reads 1,000 newtons. Well, the fact that the scale reads 1,000 newtons tells you what? Acceleration 0, therefore constant velocity. So then what happens? All of a sudden he looks down at the scale and he sees himself losing weight. But is he losing weight? No. It's just that Fn goes to how much? 600. So you have 600 minus 1,000, because that weight doesn't change. His FG is always 1,000. And that's equal to 100 times A. And what do you get here? 600 minus 1,000 is negative 400. And that's equal to 100A, which means A is equal to negative 4 meters per second squared. Now what? Now we graph it. Let's do all sorts of graphs. So, first graph I want to do is A. So here is A. That's not A. That's A. A, T. What does this look like? Let's use, I don't know, red. Is that red? All right, so perfect. So what is this going to look like? It's going to look like this, and then 0, and then we graph A, or then we graph V. And what does V look like? V looks like it goes up, horizontal line, back down. And then we graph position. So now how would I graph position here? Let me do it next to V. Notice I only need the top half to graph position. Why? It's always going up. How do you know it's always going up, Andrew? How do you know it's always going up? You're looking at the, starts with A. No, the area. He's looking at the area, and he notices that all the area is above what? The t-axis. That's right. Since all the area is above the t-axis, what does that tell you? The displacement's always increasing. Well, excuse me, the position's always increasing. So, xt. So what happens? First 2 seconds, how is this going to behave? Constant positive acceleration. What was that? That's right. Then what? Straight line. But how's that straight line going to behave? It's going to continue. It's going to be a continuation of this guy. So it's going to look like this. Maybe it's going to look like this. Maybe I should, Khalil, you need to learn how to draw graphs. Does that look right? Then what? So these are our first 2 seconds. And then this is the next 10. So this is at 12. Then what? Then it's going to start. And it's going to decrease in such a way that the slope, the final slope of this is going to be what? 0. Why is it going to be 0? Say it out. It's at rest at the end. V is 0. So there you have it. That's x versus t. Any questions? It's a great problem. But it gets better. All right. Let's see. Where are we pedagogically? I want to go back. Did we finish the Atwood yesterday? Where did we end off yesterday? I think we ended off on the cliffhanger. Yes. What is this? That was early in the class. No, yesterday it was a very special day. I did a whole series of derivations. I saw fear in your eyes. All right? So let's go. Okay. Yeah, so did we get to that ticker? No. So ticker tape. So, yeah, this is something I've been meaning to do. So ticker tape, you go, hook it up, and what are the forces acting on, well, first, what's the body that you're reading? The tape. So what are the forces acting on the tape? Let's do this. So we're only interested in what points in time. The points in time where the hammer is hitting it. So maybe we should make a profile. What type of profile would be the easiest to describe? Maybe a profile with the tape like this. In other words, the tape looks like this. Or here's the tape. But we're going to look at it like this. Ooh, that looks very, very straight. It's kind of incredible, actually. So anyhow, what are the forces acting on this little bit of mass? Gravity, but is gravity a major force on here? Yes or no? The force mostly is tension. But there is a gravitational force acting on this little bit of mass, and that's down. But really, the major force is the force of tension due to what? What was the cause of that tension? The force of gravity on that little metal ball causes tension to go throughout that tape. So call that Ft. And what other forces are acting on it? Yes. So this is the hammer, the force of the hammer. Well, I have the wall here. So this is the wall. Dig, 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 dig. All right. So now, and what else do we have? So I'll call it Fa. This is on the surface, right? That block. So therefore, it's going to apply surface forces. The obvious surface force is one that is perpendicular to it. In other words, normal. Why do you know there has to be a normal force? Because you look at that free body diagram, and where's that tape going to fly? Down and? So it would go this way, right? So you know that there's going to be a normal force. Yes? From the wall. That's right, from this metal block. Because this is ticking this onto the wall. All right? And now what else? What's the other force? The force of kinetic friction, right? Because this thing is slipping, and that's going up. How do you know it's going up, Andrew? That means the relative motion is downward, and friction is going to oppose that relative motion, so it's going to act upward. And there you have it, guys. So now, when I go and actually analyze, the forces, right, this is effectively what force? What is this force? Yes? It's gravity acting on the ball and all the pieces of tape underneath the piece of tape that we're analyzing. So we're only analyzing this bit, and so it's effectively the force of gravity on this whole length of segment. Okay? So now what is the force of friction doing? Yeah, it's retarding the motion. It's retarding the acceleration of this object. And that's why you have the error. It's the friction opposing the motion perpendicular to this surface when the hammer hits it. But now we can actually analyze why. Why using Newton's laws. Which is why I love this lab. It has great error. Fantastic error. So, now we go and do an analogous problem. And now this problem's even tougher. The question is, should I make it easy or hard? Really? It's hard enough as is. Just make it easy. Why not? Come on. All right. I'll make it hard. Come on now. I had to. No, seriously, it's up to you. How about I do both? How about I do the easy one first and then increase the difficulty? So, and guess what this is going to be? Because by now, you already know what type of systems I like. It's going to be an Atwood. But it's going to be a special Atwood.
One that we haven't covered yet?
Yes. Okay? And let's make, there's a pulley here too, of course. Of course there's a pulley. Come on. Here's a pulley. And guess what we have here? Rope. And guess what this rope has? It has mass. And let's make this table real high. And of course, you guys have all seen this in reality, right? This is something like everything else is kind of contrived. But this is something you see all the time. What is this right here? What do you see? What is this describing? This is describing any number of situations where you see some cable, right, that's like hanging off a table. And then what happens? Sometimes it will stay, and sometimes it will fall off. It's really better when you have like a chain. Like if you have a chain. Who has a chain? I have a chain. No, that's attached to me. Damn it. Come on, where is it? Chains. If you know how to get it, bring it. Well, that was what I was asking about. Do you want it easy or do you want it hard? If you want it easy, let's actually eliminate friction. Where are you, chains? Man, I'm glad we have someone who knows things. So I want to make this table a lot higher than this rope. So now I want to find out the acceleration of this thing. Well, first thing I'm going to ask you is, do you expect the acceleration to be constant, yes or no? Talk to each other. Yeah, you guys are spot on. All right, so you guys are in good shape. You know what you're talking about. It's definitely not going to be uniform. So what do I have to do? I need to go and start describing this. You have to be a little careful. Here, I'm actually, before I do a free body diagram, I want to actually construct a coordinate system. So what coordinate system is going to be the most convenient? Down is positive, and to the right is positive. And so what I can do is maybe I'll look at this. So let me give you some things. This rope, the total mass of the rope is M. Total mass of rope. And I'm going to say this is a uniform rope. What does that mean? It's made of the same material, same thickness throughout. And the rope has length L. It's the length of the rope. So what I'm going to do is I'm going to analyze one point. But I'm going to pick this point very, very cleverly. The point I'm going to analyze is this point right here. Why is that point the point I'm going to analyze? Well, realize that pulley's really small. Really, it's really small. Yes! Yes! Oh, man. This is like the greatest thing that's ever happened to me, guys. Fantastic. awesome. And you know what? I would love to use a photo gate on this. I have no idea how to do this, but let's do this again, just so that everyone sees this. This really is. And notice how little is hanging off. And yet, what is it able to overcome? The static friction or even the kinetic, like it's able to, able to overcome static friction. It's just incredible. All right. So let's take a look at this. So here you have this. That is that. All right? So what are we going to do? So I'm going to take a look at this point. And the reason I'm going to take a look at this point is because it's at the juncture for going down and going to the right. All right? So now I'm going to call this, since this is going down, where am I going to put my origin? Maybe I'll put my origin, the y-axis, down here. So this is going to be some point 1. Similarly, since that's to the right, who cares? This is fine. All I really need to know is what y is. So then how much length of the rope is on the table? How much is on the table? Yes. Very good. L minus y is on the table. So I'm going to call this piece M2. And I'm going to call this piece M1. How can I find M1 and M2? Let's see if you guys can talk about it for a second. I want you to find it in terms of things that we know, like the total mass and the length of the rope, and this parameter y. Anybody have it? You guys are close, because I can hear all the bells and whistles going off in their brains. What do you have for M1? Okay, so it's M minus M2. That's kind of correct. But let's actually think about this, right? What's the total length? Yes, Harrison. Very good. Y over L times big M.
Oh, wait, we need y?
Yes, we need Y.
Okay, that's why I'm...
Very good. So then what would M2 be? Yes. That's right. Very good. You guys are pros. You don't realize it, but I'm telling you, you're getting really good. You don't feel it because you don't think you could go home and do this, right? You don't think you can go home and bang out this problem. That's okay. You're not there yet. You'll get there. So now what do we do? Free body diagram. Which one? Let's do M1. Which one? M1. All right, so we take M1. I'll draw it here. This is M1. And where are the forces on M1? Yes. The force of gravity, so Fg1. And the force of tension, which is directed upward. Ft1. And notice, force of tension is going to be the same for M1 and M2. Why? Because we're looking at it at a point. In other words, we're only looking at it at this point. Is the force of tension going to be the same throughout the rope? Yes or no? No. Force of tension is going to vary throughout this rope. But at a single point, that force of tension is going to be the same. So let's call that Ft. And now we look at M2. And what are the forces on M2? And tension. Well, the question is, do you want this hard or easy? For right now, let's make it easy first. Then we'll do a harder, like the harder treatment. So we apply Ft to the right. What else? We have gravity, Fg2. And we have, what else? Normal force, Fn. Any other forces acting on this? Yes. Who wants to repeat? Who wants to repeat what I just said? Do you want to do the easy problem, the hard problem? Because if more people ask that, it makes me want to do the hard problem. Do you want me to do it? I'll do it. Don't hold me back. Hold me back. All right. So now. So a little heads up. I don't have to worry about the vertical forces on M2. And I want you to tell me why. Yes?
The gravitational force and normal force will be.
Okay, but why does it not matter? No friction. If friction was present, it would matter. Why? It's proportional to normal force. Don't feel like you have to raise your hand. I'd rather it just be a straight-up discussion with everyone, even if you have to force yourselves to talk over each other. I mean, it's totally non-standard, but since when is anything in this class standard? So now what do? We write Newton's second law. What do we got? Let's do Newton's second law in M1. What do we have? I can't hear you. Is that correct? Why is that not correct? Very good. So therefore it changes to Fg1 minus Ft equals M1 A1. It's better to be wrong than right in this class. It is better to be wrong than right. I'm telling you, if you are wrong, you will learn something. But if you're right, you can't tell if you guess the right answer or you know something. It's better to be wrong than right. And it's better to be lucky than smart. So, that's totally separate. Now we do net force on F2, on M2. What do we have? Well, what did I already establish? The y direction is irrelevant for this problem because we don't have to worry about friction. Yes. So what are the forces on M2? Ft. And that's equal to A2. Now, last piece is what do we do? What can we say about A1 and A2? What can we say about A1 and A2? Acceleration of these two. Why? Be a little careful. Because it's at a single point. Very, very good. See, in general, you were right. You're absolutely right. But in this case, you have to be a little careful because we're analyzing it at one point. Notice, is A going to be the same for every point along this rope? And the answer is no. And you'll see why. So we'll just say A1 equals A2 equals A. And this is M1A, M2A. And guess what we're going to do with these two? Add them is correct. So let's add them. You add them, and what do you get? Notice Fg1 minus Ft plus Ft is Fg1. And what do you get on the right-hand side? And now now notice something. This is beautiful. What's M1 plus M2?
M.
That's right. It's just big M. So here on the left-hand side, what's FG1? Which M? M1G equals big M times A. But what's M1? What's M1? Y over L times big M times G equals big M times A. Yes? Think about how we actually constructed this thing. What does big M represent? That's right. What is M1 plus M2? All right? I could also have added these two, but if I add these two, what am I going to get? Add these two. Algebraically, what do you get? M. Why? Because y over L times M cancels out that negative y over L plus M, and all you're going to be left with is L over L times M, but that's just M. So, last piece is, what's A? YG over L. So now we're going to graph it. So, what does this look like? Clearly, what am I going to graph? A versus T? Is that correct? Or A versus Y? And what is that going to look like? Thomas, what do you think? Okay, so it's going to look like, it's going to start at 0, and it's going to have a slope of, well, it's just going to increase, right? And then what? Be careful. What's its maximum value? That's right. So it's going to look like this. Because what is that? What is that going to be? That's going to be G. Notice when y equals L, what's the acceleration of this thing? G. So now here's a question. This is a really hard question. What does this look like? Careful. You're right. So it's going to look like, it's going to be parabolic. Then it's going to become, what's that called? Linear. It's going to be a parabola at first, and then it's going to become linear. Notice, what is its slope? What's the slope of the linear portion? What's that? Yes, but what is that slope equal to? The linear portion. G. That's right. This would have a slope of G. You guys are awesome. So now, yes? I could do V versus Y. I could have done A versus T as well. Because, as you see, Y, generally, I would say Y, Miss Cleo, what are you really thinking? Let me say this for a second. I can't tell you whether this will truly be parabolic or whether A versus T will truly be linear. I'm going to have to really think about that. But what I can tell you is that this is going to be some curve initially. And then that curve has to eventually become linear with a slope of G. That's the most I could say. And in fact, I have strong suspicions that A versus T looks like this. I have very strong suspicions that it looks like this. In other words, it's not parabolic. It's neither parabolic nor is it it's definitely not linear, it's not parabolic, but it's exponential. Right? It's exponential, and what is its asymptotic value? G. That's right. This is why I suspect. To be determined. And in fact, it might even be like this. I don't really know. I have to go and solve what's called the differential equation. So, any questions? All right, so then I got a question for you. What do you want to do right now? Because we have a number of different options. We can do Pear Deck. You can work on problems. I could continue lecturing, but I think you guys have hit the overload for the last 2 days. Hard Pear Deck questions? Sure. So you don't want any gimmies, right? All right, so this is, fantastic. Is this where we left off? No, we didn't get to this. This is a good place to start. This is as good of a place to start as any. Climbing up a rope. I just opened my email and like 20 emails just popped up. Everybody sent me the free response question. I really do encourage people to come in after school for help. As you can see, when you get to problem solving, things get a little tricky. Mine. Yeah, but choice 2 is just too good. All right, 30 seconds. So you guys are in pretty good shape. You guys are in pretty good shape. All right. 5, 4, 3, 2, time. The answer is 4 is correct. The rope actually pulls you up. Makes sense. When you push down, you're pushing down on what body? The rope. Therefore, the rope exerts an equal and opposite force on you. So that's pretty easy. Let me. All right. You and a friend can each pull a rope with a force of 20 newtons. You're not very strong. If you want to rip a rope in half, what's the best way to do it? 4 is correct. "30 seconds." "6 seconds." Casey. Ariana. Vincent. I'll give you guys another 5 seconds. 5. Sam. Vincent. Time. All right. So here are your responses. Clear consensus. All right. Who wants to defend their answer? Yes, Manuel.
Like that other problem that you showed us, like if two things are pointing down with the same weight.
Yes.
Force, it's just going to be that force.
It's equivalent to just simply pulling with 20 newtons. Correct. So that means it can't be.
And 1 and 3.
So wait, it can't be 1 and 3. So therefore it must be 2 or 4. Yes, 2 or 4. Yes.
Why is it that it doesn't work when you pull from both opposite ends? Because wouldn't the total force acting on it be 20 newtons? It's 20 from each side?
No, because on any particular segment of rope, the amount of force is 20 newtons. It's physically equivalent to simply just tying that rope to a tree and pulling on it with 20 newtons. The only way that you're actually going to get 40 newtons of force is tying it to a tree and both of you pulling with 20 newtons. When you do a free body diagram on it, now you're putting a force of 40 newtons on it, or double the force. So, all right. Box sits on a pickup truck on a frictionless truck bed. When the truck accelerates forward, the box slides off the back of the truck because All right, 10 seconds. 5, 4, 3, Julia, Vincent, Emily, 2, 1. Very good, guys. You're in good shape. Overwhelmingly, you picked C, no net force. The net force that you need to act on it is what? In order to keep it in that truck, what net force needs to act on it? Static friction. Anti-lock brakes, they work because? You'll need to type in your answer. Why do they work?
Static friction is greater than kinetic.
That's correct. What is anti-lock brakes? Did you just ask? Ooh, do you guys not know what anti-lock brakes are? Oh, wow. Talk about generational. All right. Anti-lock brakes is a mechanism that's in all of our cars now. And what the mechanism does is when you slam on the brakes, what it doesn't do is it doesn't lock the brakes. Instead, the way it behaves is when you slam the brakes, it goes like this. In other words, it periodically applies the brakes on the wheels. Why? it would start sliding, and since it slides, what's going to happen? It's going to be subjected to what friction? Kinetic friction. And the coefficient of kinetic friction is less than that of static friction. You want your wheels to maintain static contact to the road. And so the way you do that is you prevent it from skidding. This is why hydroplaning is so dangerous. Have you guys ever hydroplaned?
I have. Parents have.
It was the most terrifying experience of my life.
It's terrifying. What happens when you hydroplane? Huh?
It just completely skids out. You have no idea what's going on. You jam the brakes, you keep on going, and you can't steer it.
Yeah. Like even sometimes you'll hydroplane and it will be fine, and the reason is because you're traveling in a straight line. This is usually what happens. You're on the highway, it's pouring outside, and all of a sudden you just feel like the car is traveling on air. Right? It's just like, you're like, I'll slow down. So, all right, so here's a basic question. And notice the mu s's don't match. Mu s is 0.5. Don't worry about the 0.4. Mu s is 0.5. Fifteen seconds. You guys are in good shape. 5, 4, 3, 2, 1. Time. You guys are in very, very good shape. Because let me tell you something. A variation of this question is either going to appear on this exam or the next exam, and it will definitely, I am willing to bet money that a variation of this question will appear on the AP exam. And the reason is what do they want to slip you up with? There's easy bait. What's the bait? There's a force acting on it, and it asks you which way does it move. And guess what it does?
It makes you think it moves.
It makes you think it moves, but it doesn't move. So, you're in good shape. What happens if the force of tension was 45 newtons? Still not moving. You need 50 newtons at least to move this thing.
Wait, how do we know how many
Mu s times Fn. But Fn in that case is 100. That would be the maximum force of static friction. All right, this is a great question. This is a great systems question. I haven't really dealt with systems yet. I've only started. The last day, I think, of lecture will be on Tuesday for you guys. And I'm going to show you how to do...
Please have your attention for a couple of announcements. Do the freshman football game today with Delbarton. With student athletes, please help us out. Remove your cars from the lower lot. Also, good luck to all our teams playing this weekend. Tennis, volleyball, and football is at Delbarton tomorrow. They have all big regular season games. Field hockey plays at 4:30 tomorrow at Boonton in the county semifinals. And varsity boys boys soccer plays at Mountain Lakes at 2 o'clock against Delbarton. Good luck to all our squads. Thanks very much.
All right. So, little heads up, guys. This is probably where we're going to come back. I think Tuesday is going to be the last day where I will teach a lesson. And one of the nice things about Tuesday is you're going to learn how to deal with all the Atwoods and be able to solve them in under 15, 20 seconds. And I'll even give you a little hint. You might start seeing this. Here, I'll even give you a hint as to how it will be. Don't worry about this question for now. Take the hanging Atwood. If you take the hanging Atwood, what can you say about this thing? Take a look at these two masses. Which one's greater? This one, right? So what can you say about this? This would be the driving force of the system, right? What would this thing do? What would the force of gravity on this thing do? It would retard the driving force. This is the driving force. This is the retarding force. So, let's call this M1. Let's call this M2. What's the driving force on the system? Force of gravity on 2. What's the retarding force? Force of gravity on 1. That represents the net force acting on the system. So therefore, it's equal to the mass of the system times the acceleration of the system. What's the mass of the system? Times the acceleration of the system. What's FG2? M2G. What's FG1? M1G. So notice, 15 seconds. But you're not allowed to use this on your lab. You got to break out all the forces. And the reason why is because on the AP exam, they may ask questions that involve the individual forces. You can't use the systems approach.
Do you want that sheet for classes? Because we were going to throw it out.
What?
It's like useless to us.
Dude, this is the greatest thing I've ever seen.
The other thing I want to show you is that one problem reminds me of this one chip.
Yes. Oh, yes. Yes. Oh, it's so good. It's the target truck. Oh no, this thing is awesome, and it's such a good. It's like. Remind me, I might have you guys work on the problem with friction. Doesn't change things much, but it makes the problem more interesting. Later, man. Have a great weekend.